Hello and welcome back at the third session of Protocols and Models. At the other two sessions, we discussed about the rules of the communication and about the protocols when we had the network protocol function and an overview about the network protocol, and even we discussed about the protocol suites, about the TCP/IP protocol example, and we discussed even about the reference models, where the most common was the OSI reference model and the TCP/IP protocol model. So, and in this session, we will be focused at data encapsulation and data access. So let's go and check about them and get more info about those. Just imagine this. In a theory, a single communication, such as a video or an email message with many large attachments, could be sent across a network from a source to destination as on one massive, uninterrupted stream of bits. Well, however, this would create problems for other devices that need to use the same communication channels or links. Even so, the large stream of data would result in significant delays. And for more, if any of the links in the interconnected network infrastructure failed during the transmission, the complete message would be lost and would have to be retransmitted in full. How can we fix that? A better approach is to divide the data into smaller, more manageable pieces to send over the network. Segmentation is the process of dividing a stream of data into smaller units for transmissions over the network. Even more, segmentation is necessary because data networks use the TCP/IP protocol suite and send data in individual IP packets, where each packet is sent separately, similar to sending a long letter of series of individual postcards. Packets containing segments for the same destination can be sent over different paths. And this leads to segmenting messages will have two primary benefits. The first benefit is that it will increase the speed. Because of large data stream is segmented into packets, a large amount of data can be sent over the network without trying up a communication link. This allows many different conversations to be interleaved on the network called multiplexing. And the second benefit is that will increases efficiency. If a single segment will fail to reach the destination due to a failure in the network or network congestion, only that segment needs to be retransmitted instead of resending the entire data stream. So if we can see in the picture, you will see that the segmentation, so the whole message will be sent in packets, and as we said before, that will allow many different conversations to be interleaved on the network called multiplexing. So in this case, both workers will send data to the server, for example, will save their data to the server. So that what is the importance of segmenting the whole message that need to be delivered. So there is a challenge at the segmentation and multiplexing transmitted message. So we will get an analogy and we will check this analogy and we will think about what will happen even in a real network. So the challenge to use segmentation and multiplexing to transmit messages across a network is the level of complexity that is added to the process. So let's compare this. Imagine if you had to send a 100-page letter to the destination, but each envelope could only hold one page. So the envelope in this case is the packets. Therefore, 100 envelopes will be required, and each envelope would need to be addressed individually. It is possible that this 100-page letter in 100 different envelopes will arrive out of order. Consequently, the information in the envelope would need to include a sequence number to ensure that the receiver would be able to reassemble the page in proper order. So, in network communication, each segment of message must go through a similar process to ensure that it gets to the correct destination and can be reassembled into the content of the original message. And as it is shown in the figure, so there are both of the workers that need to send the message to the destination. So each of them will label their package, and the destination will be able by the IP address and by the label number to understand that the message is coming from the first or the second source. And if it comes, for example, from the first source, by getting the label number, it will be able to understand the order of the packets that will come. And in this case, by reordering them at the destination, we'll be able to understand the message that came from the source. So, who is the responsible for sequencing the individual segments? In this case, is the TCP protocol responsible for that. And the TCP protocol is the protocol at the network level. So we will see that as the application data is passed down to the protocol stack on its way to be transmitted across the network media, various protocol information will be added at each level. And this process is known the encapsulation process. And this process is explained at this figure. The most important thing that you need to remember is that the form of a piece of data that takes at any layer, it is called the protocol data unit, or as a PDU. And during encapsulation, each succeeding layer encapsulates the PDU that will receive from the layer above in accordance with the protocol being used. And at each stage of the process, a PDU has a different name to reflect its new function. Even they use different kind of level and different kind of suites, we will be focused at, and we will be named the PDU depending on the protocols of TCP/IP suite. And as you can see in this figure, the PDU for the application layer is called a data. So it's the data from the source. And as the PDU called data in this case will go down to the transport layer, it will have the header of the transport added to the data. The transport header may be the header of the TCP protocol, and as it is in this case, it is called a segment. The PDU is called a segment, but if the transport header will be the UDP protocol, the header of UDP, the PDU in this layer will be called a datagram. As the PDU from the transport layer, that is called segment, in this case, will go down to the network layer, the network layer will get this PDU, in this case will get the segment, and will add the header of the network. The header of the network is the header of the IP address, where it is the IP address of the destination and the IP address of the source. And in this case, the PDU is called a packet. And as the packets will go down to the data link layer, where in the data link layer will be added the frame header and a frame trailer. And the frame header will be the header of the MAC address of source and the destination. So the frame is the name of the PDU at the data link layer. As the PDU will go down to the physical layer, the PDU will be called bits, because in this case, all the information, all the PDU will be converted into bits so that can be able to transmit over the medium. So as you can see here, the data that is captured from the application layer, and each layer, it is added the header of the layer. So, and as you can see, the PDU will change the name depending on the level that, at the layer that it is. So this is the process of the encapsulation and the name of protocol data unit named in each layer. I don't think that it is hard to be remembered. So in this slide, there is explained, or it is shown as an animation, the process of the encapsulation and de-encapsulation. And there are two examples. The first example is about the encapsulation, as we saw further, the process when the PDU go down from that application layer to the physical layer, all the process that went down, and even the name of the PDU called in each layer. And at the second session is the de-encapsulation process and how it will be de-encapsulated, and is the reverse process. So if during the encapsulation, as the PDU will go down and down, it will be added the header of each layer. And in the de-encapsulation process, as it is as I said, is the reverse process, you will see that as the PDU will go up to the application layer from the physical layer, the PDU will be smaller and smaller, because in each layer the header of that layer will be removed. So as you can see, the first one, an encapsulation process, header, it will add the header of the layer. As it goes down, then in the network layer is the IP header, and the Ethernet will be we'll call the frame, will be the MAC address header. And at the second one is the reverse process, but then it is called de-encapsulation. And as the PDU will go up, in each header will be removed the header of that layer, and at the end it will be only the data, and you can see that is the same message that was at the source. So as we just learned, it is very necessary for the message that travel across the network to be segmented. But those segmented messages will not go anywhere if they are not addressed properly. The network and data link layers are responsible for delivering the data from the source device to the destination device. And as it's shown in this table, the protocol at both layers contain a source and a destination address. But their addresses have different purpose. So we have the network layer source and destination address, who is responsible for delivering the IP packets from the original source to the final destination, which may be on the same network or even in the remote network. And the data link layer source and destination address are responsible for delivering the data link frame from one network interface card to another network interface card on the same network. An IP address is the network layer logical address used to deliver the IP packets from the original source to the final destination. And as it is shown in this figure, this is the PDU of the network layer or the PDU of layer 3. And it has the PDU from the transport layer and the header of the network layer, so the header of the IP packet. And each IP packet will contain two IP addresses. We'll have the source IP address, where is the IP address of the sending device, which is the origin source of the packet, and we'll have even the destination IP address, where is the IP address of the receiving device, which is the final destination of the packet. And the IP address indicates the original source IP address and the final destination IP address. And this is true wherever if the source and the destination are in the same network, same IP network, or in the different IP networks. And it is important even to remember that an IP address will contain two parts: the network portion in IPv4 or the prefix in the IPv6, which is the leftmost part of the address that indicates the network in which the IP address is a member. All devices on the same network will have the same network portion of the addresses, and they have even the host portion in IPv4 or interface ID in IPv6, which is the remaining part of the addresses that identifies a specific device on the network. This portion is unique for each device or interface on the network. So let's see this example here where PC1 is trying to communicate with an FTP server and they are on the same network. So the packets here that it's sourced from the PC1 for the destination FTP server will have the IP address of the source and the IP address of the destination. IP address of the source, it is 192.168.1.110, and the IP address of the destination is 192.168.1.9. And as you can see, the network part in both devices, so at the source and the destination, is the same. And what is unique for them, it is the host portion. In this case, for the source, it is 110, and for the host of the destination, it is 9. And this is unique for each devices. In the case that the sender and the receiver of the IP packets are on the same network, where the data link frame is sent directly to the receiving device on an Ethernet network, the data link addresses are known as Ethernet Media Access Control, or as MAC addresses, and it is as it is highlighted in this figure. So the MAC addresses are physically embedded on the Ethernet network interface card. The source MAC address is the data link address of the Ethernet MAC address of the device that sends the data link frame with an encapsulated IP packet. The MAC address of the Ethernet network interface card for PC1 is all A's. And the destination MAC address is when the receiving device is on the same network as the sending device. This is the data link address of the receiving device. And as it is in this example, the MAC address of the destination device is all with the capital C letter. The frame with the encapsulated IP packets can now be transmitted from PC1 directly to the FTP server. But what happened with the roles of the network layer addresses and the data link layer addresses when a device is trying to communicate with a device on the remote network? Where is the difference here? And for analyzing this, we will have an example of a client, in this case the PC1, try to reach a web server that is in a remote network with a different IP network address. And when the sender of the packet is on a different network from the receiver, the source and the destination IP address will represent hosts on different networks. This will be indicated by the network portion of the IP address of the destination host. So as you can see in the figure, this is the source IP address and this is the destination IP address of the Ethernet frame, which is encapsulated, the IP packets. And the IP address of the sending device, it will be the 192.168.1.110, and the IP address of the receiver, which is the web server, will be 172.16.1.99. And as you can see at the network portion, we will see that the IP address is different. So when the sender and the receiver of the IP packets are on different networks, the Ethernet data link frame cannot be directly sent to the destination host because the host is not directly reachable in the network of the sender. The Ethernet frame must be sent to another device known as a router or a default gateway. And in the example that we have, the default gateway for the network that the PC1 is connected is the router 1 and has the Ethernet data link frame address that is one on the same network as PC1. And this allows the PC1 to reach the router directly. The source MAC address, in this case, is the Ethernet MAC address of the sending device, which is the MAC address as all A's. And the destination MAC address will not be the destination MAC address of the web server because it is not reachable, because it's not directly connected with the PC1, but will be the MAC address of the router, the gateway. And in this case, the MAC address, as it is shown, it's all ones. The Ethernet frame with the encapsulated IP packets can now be transmitted to the router R1. R1 will forward our router will forward the package to the destination web server. This may mean that router 1 will forward the package to another router or directly to web server if the destination is connected directly with our router, with R1. But since it is not connected, it will go through some steps, and you will see that it will change the MAC address as it goes the packet to the destination. The logical addresses or the IP addresses are responsible for delivering the package from source to the final destination. But the data link layer or the physical address has a different role. The purpose of the data link addresses is to deliver the data link frame from one network interface to another network interface on the same network. Before an IP packet can be sent over a wired or wireless network, it must be encapsulated in a data link frame so it can be transmitted over the physical medium. So let's see the first step. So the source and the destination are not at the same network. So the first step is the MAC address will be the MAC address, the destination MAC address and the source MAC address on the same network. So as the IP packets travel from host to the router or router to router and finally router to host, each point along the way the IP packet is encapsulated in a new data link frame. So at the first frame with the host to the router, it will be the destination MAC address of the router connected directly and the source MAC address of the PC1. And as the packets reach the router 1 to reach the router 2, you will see that the layer 3, which means the IP addresses, the source and the destination IP address, will not change. That will be the same, but what will change, it will be that the destination MAC addresses will be different. When it goes from router to the router, the source MAC address will be the MAC address of the router 1, and the destination MAC address will be the destination MAC address for the router 2. So as you can see, the MAC addresses will change because they will have the MAC address of the directly devices. And when finally the frame will reach the IP address of the destination, so the network of the final destination, you will see that the source IP address and the destination IP address will be still the same, but what will change, it is the MAC address. So the source MAC address will be the MAC address of the final router, and the destination MAC address will be the MAC address of the final destination in this case. So as we said before, the IP packets travel from host to router, router to host, and finally router to the destination. And each point along the way, we said that the packets will be encapsulated in the new frames, and we saw that the header of the IP packet was the same, so the source IP address and the destination IP address didn't change at all, but each data link frame, the new data link frame as the packet was traveling, had different header, had the source data link address of the network interface card sending the frame and the destination data link address of the network interface card receiving that frame. The layer 2 data link protocol is only used to deliver the packets from network interface to network interface on the same network. The router removes the layer 2 information as it received on one network interface card and adds new data link information before forwarding out the exit network interface card on its way toward the final destination. The IP packet is encapsulated in a data link frame that contains the following data link information: source data link address and the destination data link address. And as we said, this keep changing in each hop that they were trying to reach the destination. With the third session, we ended up all the topics about the protocol and models. Hopefully they were very understandable by you, and please do not forget to subscribe at my YouTube channel AA Networking, and see you at the next section that will come up next Monday. Thank you and have a good day.